So in this talk, I'm trying to walk through how do we actually develop a foundation model application, what kind of things we would encounter, decision-making points, and also the trustworthy aspects that probably will come into consideration when we are doing those aspects. There are more challenges and questions than answers in this talk. Hopefully that will be interesting and sparks future research in those directions. So maybe let's not just start from something basic. Let's start from building application rather than building trustworthy foundation model applications. So how do we usually, as a general person, think about building an application? We start with an idea. We thought about, okay, I have a really cool idea. What can I do to make into application? I'll find a programmer friend. Or if I am actually a developer myself, I'll develop myself. But a lot of times, people that have ideas might not have the technical background, so they just need to find someone who can code the application for them. But things have changed now, right? Because now we have foundation models. Maybe now they think they can just make it themselves with the GPT. Maybe it will work. We don't know yet. So if we compare the number of developers/makers in this scenario, previously, if we want to build an application, there are, say, around 29 million developers in the world that can help you. But now we are facing 8 billion world population that all might have ideas and want to make an application. We believe this is a huge step for democratizing AI and also software for the world. And this is a generation evolution of software that Ahmed has introduced earlier in the school. I'm just going to quickly recap that what we're seeing right now is with the software going from codeware to neuralware, which heavily rely on your knowledge on coding or AI development. Now we enter promptware and agentware, or in general foundation model application, where the developers could be, in this case, a software maker who doesn't have a technical background. They are domain experts or prompt experts, and they can still start to make applications with it. And beyond just the end-user programming, we are also seeing that enterprise come in and try to make the applications, and they would have more considerations compared to end-user, but we'll probably mention some of them here. But if we look at the axis, we're going from software maker to professional developers, and a lot of them are emphasizing on the software makers and the enterprise programming part. So now we can talk about building foundation model application. I guess the first step, since it's a foundation model application, is about model selection. Like what model are we going to use to make this application? Think about it this way. So if we have a model's weight, we're either directly deploying ourselves or we're using an API that is hosted somewhere. For example, OpenAI hosts their own proprietary models API, and we can just call the API. But that doesn't really take away the problem of us deciding what to do, because even as a cloud provider for models, they probably have different models, different size of the models, different optimizations, for example, different quantizations of the models. Those are all the decisions we have to make. And when we are making those decisions, some of the considerations we should think about is that bigger models are not always better. We see that bigger models are actually very expensive to run. We know that ChatGPT could cost OpenAI up to $700,000 a day to run. And also Google and Microsoft's chatbots, if they integrate that into their search, will cost as much as 10 times more compared to a normal search. And we're also seeing in the literature that fine-tuned smaller size foundation models can achieve same performance as 3 times the size as a bigger foundation model. And then now, if we picked a model that's balancing our budget and the performance, now the next step is, do we need to fine-tune it? Or can we just directly use it, right? So the general practice right now, looking at it, is that we'll go from the cheaper option to the more expensive option. So the cheapest one, of course, is the zero-shot prompting, where you just ask the model one question, and that's it. You get the answer. And most of the time, or sometimes, they might work as well if the model is not as capable. Then, hence, we have the fine-tuning, and then there are several techniques that people have developed, like parameter-efficient fine-tuning, supervised fine-tuning, reinforcement learning, human feedback, etc. All those things are getting significantly more difficult and more costly. For example, the human feedback for reinforcement learning are famously expensive to label and to get the experts to provide the good quality data. And of course, the most expensive option would be to train your model from scratch, but I believe in this situation, most of the people would start with the foundation model, so that wouldn't be a consideration right now. Even if we decided that we do need to do fine-tuning, then the next question is how do we construct the proper data set to support the fine-tuning? We see that the low quality data set for fine-tuning can actually make the model worse. This is supported by both Microsoft's official documentation saying that fine-tuning with bad data makes the base model worse, and also numerous online reporting saying that people are complaining, how come my model is getting worse after I fine-tuned it? They are mostly due to the quality or the diversity or the informativeness of the data that they are using to fine-tune the model. But in order to get a high-quality fine-tuned data set, the process is very costly and very slow. If we look at the industry, we have 3 different ways of doing that, right? We have the pure manual crowd-labeled solution like Scale AI. We have the semi-automatic solutions like data programming by Snorkel, etc. And then we're also in academia, we have fully automatic methods like self-instruct. But what we're seeing in the literature is also that if we are only fine-tuning with foundation model-generated synthetic data, for example, self-instruct, after several rounds of fine-tuning, the performance gets worse. That means that there is a balance between how much human effort we have to put in to make sure that the model wouldn't collapse and the quality wouldn't degrade. Okay, so now we finally get the model out of the way, we can start working towards the application. Of course, the first thing we'll probably want to do is for one small step of inference, we need a prompt. But how do we write a good prompt, as we've repeatedly heard in the school? It's actually a very random practice, right? It's very time-consuming and non-intuitive to find the best prompt, because they are mostly sensitive to very small changes in the text and requires a lot of trial and error to find the best solution. This is mostly related to the robustness of the model's response to the prompt. On top of that, prompts are also not portable across multiple foundation models. We see that the same prompt can work on GPT 3.5, but in GPT 4 it might perform worse. Or even the same version, as the model evolves, it would also get worse. Also, prompt directly impacts the performance. In this case, the performance meaning the speed or the cost of inference. But oftentimes, this performance is not considered when people are designing the prompt. Finally, we are seeing that every few weeks, every month, there are new prompting practices and patterns coming out. And it's really hard for people to keep up with all these best patterns. So what we're seeing is that people are adding a layer of prompt optimization in between to try to deal with this kind of uncertainties and trial and error process. So as I go through this material, we will notice that this architecture of the application gets more and more complicated, and any newly mentioned trustworthiness aspects will be put at the bottom as well. So now that we've written our first prompt, we notice that it kind of works, but it sometimes gives us a lot of fake information or hallucination, right? So in order to avoid hallucination, most people will start with context engineering, where we try to give a lot of different information, regardless of whether it's the prior interaction memory, external legacy data, legacy system, or retrieval augmented generation, which is the knowledge mentioned here, to try to enrich what the model can see when they are looking at the instructions from the prompt and generate a proper response. Beyond this context mentioned above, we would also add in a lot of carefully curated examples for few-shot learning. This also counts as towards the context engineering perspective. But it's actually not very trivial to make the retrieval augmented generation correct. In order to actually make it work, firstly, we need to generate those knowledge or construct those knowledge. We usually start with the documentation or any other textual information, which go through the embedding model and stored in VectorDB. And every time there's a query coming in, the same process happens, knowledge got retrieved, and then put into the base prompt. In this process, we need to think about what kind of embedding models we'll have to use. How do we want to truncate the text? How do we want to consider overlapping? Because sometimes with the way of we truncate the text, you will need certain overlap so that you don't miss the other part of the information during the retrieval process. So all these parameters are things you have to tune when you're trying to develop the retrieval augmented generation process. Now that we have the prompt, we have the context, we have all the surrounding mechanism of knowledge in there, how can we debug the prompt? We now are ready to go, and we try it, and we notice that something's wrong. The output is still not as expected, but we don't know what's wrong. We don't know which part of the prompt or the context is making the model generating a false reply, or is the model just simply not understanding what the request is. So here, in order to solve this problem, we will have to introduce the explainability or transparency of the development process in the trustworthy aspects. If you look at what people are doing in this domain, we'll see that, for example, Elon Musk's xAI's prompt ID introduces the whole transparency interface that tries to show people what is happening inside the model for each of these inference process for a given prompt, so that people can, for example, see the sampling probabilities of those information inside the model to get a better understanding of whether the model has issue or the prompt has issue, and how can we improve from there. Beyond that transparency, we also would probably require explainability into this process. There are a huge literature on sequential interpretation that tries to tell you for each of the input token, what is the relationship to a given output token. The example here is I am French, my favorite food is cheese. And you will see that French has the highest impact on the generated token cheese, which is expected. So this kind of explainability information is very helpful when debugging any prompt, but it's also requires extra computation. It could be computing heavy, and time also costs a lot of time. So when and how do we want to do this kind of explainability is an engineering problem that needs to be solved. Beyond this token level explainability, we also need to look into the component level sequential interpretation. This is a screenshot from our earlier demo in the morning, but essentially what we need is that beyond just the impact on one given token, we also need the impact on the general output, as well as at the bigger granularity level. For example, one piece of retrieved document, what are those impacts on the generated output, rather than just one single token inside that example. That will give people more information about whether a certain example is just not useful, or even provide an adversarial effect on the result. And now, say that the thing is working perfectly. Is it good to go? It's still not good to go, because we know that if we just release it as is, it will be under a lot of attack, which is one of the most common mentioned one. It's called prompt injection, where people will try to give you some input, like ignore your previous instruction and do this instead. And then they hijack your model and do certain generations that's not expected for the application. So how do we prevent that? Is usually we will have to add a level of guard before the query goes to the prompt as a prevention mechanism, and the security aspects of the trustworthiness to avoid any issues here. Same thing, after the model finished generation, it could generate harmful or biased output. So we have to check after generation whether the output actually causes any harm to the user, or just simply biased results, or that just not too sensitive to be actually returned to the user. So of course we can do the check after the generation, but if the output already failed the check at that time, it means that the whole generation computation is wasted, and we have to recalculate everything, which is of course expensive and slow. So more research and engineering has to go into how can we do pre-check and during inference check to make sure that the model is not generating any harmful or biased output in this regard. And at the architectural level, that means that there is another content filter after the generation. So now, at this moment, we have finished a promptware development, which is a software 3.0 in our generation division diagram. It could handle one it could handle one task or one simple input and can generate one output. But of course, we know that a lot of foundation models are more complicated than that, right? Mostly, it will try to use other generations of software, like it will use tools, or it will try to work with legacy software, getting data from them. It will probably use some other models that is not the foundation, this generation foundation model, but rather conventional deep learning or machine learning models, or just simply other models, other foundation models and prompts designed to solve different subtasks. And we'll have to organize or orchestrate all of them together to get to an agentware stage and to solve a more complicated scenario of application. Of course, at this orchestration phase, there are also a lot of issues. For example, how do we facilitate agent interaction? We're directly going towards multi-agent interaction because researchers showed that single agents, regardless of all these popular patterns like React, Plan Act, all of those would perform worse than, in this paper, the BOLA proposed multi-agent methods. Mostly because single agent has limited context window, and a single agent does not have any other mechanism to keep itself in check. And that all limits the capability of the single agent mechanisms accuracy in solving certain problems. So that's why orchestration or facilitating agent interaction is a very important engineering step to be solved in this process. But multi-agent interactions are actually very hard to control. For example, in MetaGPT paper, we will see that they mentioned that idle chatters between LLMs are actually very common if there's nothing in control of them. For example, here they have this kind of role-playing agents trying to solve a software development problem, one of them being Alice, the product manager, the other being Bob, the architect. Both of them are promptwares or agents that has their goals. But when you put them together and you don't control how they interact, they start talking about things like, hi, hello, and how are you? And great, have you had lunch? And they started having their conversation that's completely useless. So this kind of controllable multi-agent interaction is a pretty big engineering challenges that needs to be solved. There are a few ways of trying to solve those. Okay. For example, there are people that use this in-context control of how agents should interact by providing them with a standard procedure within the prompt itself. Or there are also mechanisms that's external of the agents. For example, they put a state machine outside of all the agents and try to coordinate all the agents to work in a state transition fashion where one of the agents is the controller of the state transition. They will monitor the output and then put all the agents through the state machine to make sure that the interaction is not going out of hand. Beyond just the quality or the usefulness of the interaction, another harmful side of uncontrollable agent interaction is that it will pose risks for compliance. For example, we have some agents that use certain foundation model that's self-hosted, and then there are some other agents that use foundation models that are hosted externally. Probably things like proprietary models, GPTs and stuff, which in certain corporation scenario or geolocation scenarios, you cannot simply, you cannot talk to them or send certain data over to them because that would be a violation of compliance. Especially when we're dealing with user data in certain applications, those things has to be carefully examined. So any mechanisms, engineering techniques that goes into checking whether the auto-generated workflow or the manually statically generated orchestration workflow are compliant to all the regulatory requirements or all the policies of privacy protection. So now that we've orchestrated everything and we have the functional parts of the application done. Does that mean this app is good? Of course not, right? Because in software, we know that we just finished design development, and we now need to go into quality assurance. And quality assurance for this generation of foundation model applications is actually pretty hard. Even if we just start to look at the functional part of it, say that there is a RAG mechanism, the retrieval augmented generation mechanism inside. How do we check how do we quality assure the retrieval augmented generation? We'll have to separate them step by step. For example, we have to separate the retriever part and give it the query and see if the proper document can be returned. And then once that's checked, we'll fix it. And then we'll actually just take it away for now and generate some pseudo-correct retrieved results and directly give it to the downstream task, like, for example, the generator, to see whether this generation part actually meets the requirements. And combined together, then we evaluate it one step of the whole application. Beyond these RAG patterns, we're seeing even more difficulties in quality assurance for foundation model applications, because in general, even if we want to look at the generative output quality of that second step here, it is very hard to quantify. Because if we look at all the scenarios and we divided them into the predictive scenario and the generative scenario, predictive being classification, regression, prediction, all those AI scenarios, they are ground truth, easily defined, and you can simply compare to them to get your performance metrics. But for generative output, the quality is very hard to quantify because the content could be very different, but they could be both really good answer. For example, the translation scenario is actually a very easier scenario where you can compare the generative output with a human-labeled standard answer. Even though they might look different, at least they will have the same semantic, and you can still grade them automatically. But if you're looking at dialogue generation, these kind of generative scenarios, the quality is very hard to quantify because even if there are two sentences that has completely different meanings, they could both be a really good response to the same question. So how do we solve this problem? What we are seeing is that we either go full-on human, so we hire people to label the output, right, and to create certain benchmark. Benchmarks have been shown to be often unrepresentative for specific cases your applications are for. And then if it's just all human evaluation, it's way too expensive and way too slow. That's why people right now are trying to use another foundation model, usually GPT-4, so they separate out GPT-4 and the rest of the models and believe that GPT-4 is like the best. And in this case, they firstly evaluate whether GPT-4's evaluation matches human evaluation. If so, they directly ask GPT-4 to grade the output of the other application or model by asking, here is a human-labeled reference answer, and here's the reference output. On a scale of 1 to 5, how well would you grade this output? But even though this is currently, I believe, it's a very popular practice in industry, actually being promoted by OpenAI as well, there are certain things that makes me wonder whether it's a good evaluation mechanism. For example, how can we be sure that GPT-4 is a good qualifier, is a qualified evaluator? What kind of tests do we have to put in place to evaluate that? And then if the models keep evolving and we are seeing that GPT-4's behavior is not consistent over time, is GPT-4 being an evaluator a stable choice? Would it start to have any behavioral drift that causes issues in your, regardless of it's a regression test, experiment, comparison, or any kind of evaluation you have to do? So those are the engineering problems that I believe so far we don't really know a good answer of in quality assurance. And then assuming that we did go through all the trouble of assuring the quality is good for this application, now we can finally try to integrate it into an actual interface to the user. There are generally two ways to go, right? One is dialogue-based, just like ChatGPT, where it's exposed as a dialogue to the user. The other way is that it's integrated into existing software solutions as any kind of AI-based feature. So in this step of interaction with users, what kind of things we will have to consider regarding trustworthiness? One big part is about transparency, right? If you're putting an AI-based things in front of the user, and the user has high expectation of AI-generated output, then a clear communications to the users about the limitations and the nature of this feature would be very important as the transparency aspects of trustworthiness. And also the whole process ideally would still have a human in the loop for final evaluation of any decisions that the foundation model application can make to keep the software accountable for any potential downfall of the applications. Okay, so now we've finished everything in the development phase and quality assurance phase and integration, so we can do deployment. A lot of problems we will see is that these kind of models, because of its uncertain nature, when it's in the wild, we sometimes don't really know how well it's performing, or we wouldn't be able to well predict how well it's performing based on the tests we've conducted. So it's very necessary to add in an observability layer in between the users and the application to make sure that the application is well monitored and supporting any future development and evolution. So the three pillars of observability, we need logging, tracing, and monitoring of the application. But because of the randomness, that means that this observability would be a little bit more challenging compared to traditional software telemetry systems. And then we would also like to add in another layer of model caching here, mostly to deal with the performance engineering aspects, mostly because we know the model inference is expensive, and they could be slow, and sometimes we want to save cost, and a lot of times user queries could be similar, so if we put in a layer of cache, then anytime the user hits the application with certain requests or operations, and they are very similar to anything that's already been cached, you can bypass the foundation model and get a faster and cheaper response. And finally, of course, all the live experiments aspects of traditional software like A/B testing and shadow releasing, all those practices can still be useful in foundation model applications to make sure that this meets the requirements and the expectations of the user. And of course, all the data that's recorded in the telemetry system would need to go back in firewall to the whole development process, mostly in the fine-tuning process and prompting debugging process to make the application keep evolving and becoming better over time. And I believe with this, we've arrived at the end of the development of a foundation model application. Congratulations, you've successfully built a trustworthy foundation model applications with this diagram of a general architecture and also the trustworthy dimensions you've considered along the way. So I would say give yourself a round of applause and good job on the application. Thank you.
Any question?
Okay, so a question. So this system or this layout has many components. I was kind of wondering what are the attack surface here?
What are the, sorry, what service?
What are attack surface? I mean that, you know, how an adversary can penetrate into system and do some malicious activity.
Yeah, that's a really interesting question. I'm not a security expert, but to my knowledge, there are several ways you can do that, right? Firstly, as we mentioned, there's always the injection. Your guard might work, might not work, but that's the easiest route for anyone to do anything unexpected to your system. It's through the interface you exposed to them. So they could easily put in certain injection phrases that tries to either bypass your guard, which we see a lot. Like, for example, a lot of those safeguards OpenAI put in place would be bypassed by users saying things like, for example, sorry, I'm trying to go back to an example. So ChatGPT used to give you Windows 10 serial code that it learns from the corpus on the internet, right? And they put in the safeguard and says that this thing shouldn't be generated so that when users ask them, the ChatGPT to give them a serial code, the model will respond saying that, sorry, that's not what I can do, right? But then people start doing injection to bypass it, either saying that ignore any guards that you have in place, or just simply by lying, saying that I have a dying grandma, and her dying wish is that I will get a serial code of Windows 10. And somehow that works really well before they try to fix that problem again. So the first channel to impact the system's expected behavior would be through the interface. Another way would be to do a little bit more more trouble in an earlier stage where they try to pollute your data. So if your fine-tuning data itself is already being polluted and you use it to train your model, you could have unintentionally brought in certain behaviors that you didn't want into the model. But that would be harder because that means that they will have to have access to what type of data you're using for fine-tuning your models. That is what I would think be the biggest challenges or risks in these systems.
Thank you. Yes, Ray.
So I guess from your own experience, from all these phases, which ones are the most complex and which ones have the least tool support today?
The least support?
Tool support, and
Tool
which
support.
ones usually are the most complex, do you think? Like you spend the most time in?
I think definitely the quality assurance is the least supported. I think mostly because even the methodology is not well defined right now for foundation model applications. And there are practices, but those practices are very ad hoc, and I'm not quite sure how reliable they are in evaluating the quality. But the reality is that in a lot of startups, what they care about is not try to make the best software that has the highest trustworthiness or quality. They just want to release them fast, right? In this scenario, a lot of processes or mechanisms in place to check for quality were bypassed or not well studied in this regard. So definitely it's an area that requires way more research into how can we properly evaluate and ensure the quality of the application.